Start the lecture. Yep, that looks like it's going. Okay. This is almost everything that we're covering today. I think we have some example proofs and then one more substance proof, and then that's it for today. So should be a relatively short day. All right. First new definition. Let an be some sequence, and let n sub k be a sequence of numbers, a sequence of increasing natural numbers. So 1, 2, 3, 4, or 2, 9, 15, 27. They're just natural numbers, and they're always increasing. The next one's always bigger than the previous one. So we have some sequence an, that's just some sequence, who knows. N sub k is a sequence of natural numbers that's always increasing. The next one is always bigger than the previous one. That is n sub 1 is less than n sub 2 is less than n sub 3, dot, 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 all the way through the whole sequence. Then the sequence b sub k, where the kth term in b is, okay, that's kind of a mouthful. Let's draw a picture and then come back to this definition. So a sub n, give me some sequence.
Some sequence.
We'll just say it's equal to 1 over n. All right, so what's the first term in the sequence?
1.
1 over 1, then we have 1 over 2, then we have 1 over 3, then we have 1 over 4, etc., right? And we can keep going. Okay, n sub k is just a sequence of increasing natural numbers. So give me a natural number. 2. Give me another one that's bigger. 4. Give me another one that's bigger. 8. And we can keep on going on. It's just some sequence of increasing natural numbers. So now we're defining what's called a subsequence. So a subsequence, b sub k, how does b sub k work? We're going to make the kth term in b sub k the a sub nth sub kth term from this sequence. So we are going to create a sequence from this sequence, just choosing elements in it. We're going to come along and we're going to say, I want that one, and that one, and that one. And we're going to go on picking infinitely many out and putting them into what we're going to call subsequence. Which ones are we going to pick? We're going to pick these ones. So my b sub k, my b sub 1th term, is equal to my a sub n sub 1th term. What was my n sub 1th term? That was 2. So this is going to be the same thing as a sub 2. And so my b sub 1 term is my a sub 2 term is 1/2. It's just a law of notation, but the idea is actually pretty simple. So try and get your head around both. So let's do the second term in B. b sub 2 is equal to n a sub n sub 2. What's n sub 2? 4. So that's the same thing as a sub 4, which is what? 1/4. So the next term in here is 1/4. You follow me? So what's b sub 3 going to be? So b sub 3 is going to be a sub n sub 3.
Oh.
What's n sub 3?
Oh, it's going to be 1/8.
Yeah. So n sub 3 is 8. So it's the same thing as a sub 8, which is 1/8. So basically, if you give me some sequence, and you give me some sequence of increasing natural numbers, I can then create a subsequence of the initial sequence. You see? It's pretty simple, but a lot of notation going on. Now sometimes, instead of writing it as b sub k, we just write it as a sub n sub k. That's typically how we write it. So if this is a sub n, then its subsequence is a sub n sub k, where n sub k is still just the sequence. You see how this is the exact same thing? So when we're doing some proof and we don't know anything about our sequence, but all I know is that my sequence has a subsequence, I might write something along the lines of, let AN be a sequence, comma, and let A sub n sub k be a subsequence. That's typically how it will come into context. Make sense? Question. Can A sub n be a subsequence of itself? Yes, it can, right? Where we just choose this sequence, n sub k, to be all the natural numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. Then it is just a subsequence of itself. Another thing that's worth noting, not sure where I pointed out, but notice that A sub n plus 1 is also a subsequence of A sub n. If A sub n is this, what's A sub n plus 1? What's the first term in here? 1/2. What's the second term? 1/3, etc. So you see that A sub n plus 1 is just A sub n without the first term. So it is a subsequence. And remember, subsequences still have infinitely many terms. So the intuition for what a subsequence is we just go through every term in our sequence, deciding whether or not we want to have it in a subsequence. Yes or no? And as long as you can create some sequence that way, it's a subsequence. Okay, so now let's read the exact definition and see if you have any questions. A and B subsequence, and let n sub k be a sequence of increasing natural numbers, that is n1, the first term is less than the second term is less than the third term, etc. Then the sequence B sub k, where the kth term in B is equal to the A sub n sub k term in A, is called a subsequence of A sub n. It's a mouthful, but you understand all that?
Why is it a necessary condition that the natural numbers are increasing?
What we're saying is you can't keep picking the same term over and over again, or you can't change the order of the sequence. So for example, if I let you pick the numbers, if we did 5, 2, 5, 5, 1 as our first terms, then it's no longer going to be a subsequence. Because now this sequence is going to be 1/5, 1/2, 1/5, 1/5. That is not a subsequence. I cannot go along in here saying yes or no, include it, and go through the next one iterating like that and create this sequence. So you have to go from left to right in your sequence, just choosing yes or no, do I want it, put it in or don't put it in. And the reason that we do that is because then, however this thing tends, if it's a subsequence. Notice that we know that this sequence gets closer and closer to 0, so any valid subsequence of it is going to do the exact same thing. Both sequences tend towards the same way, and that's a property you want subsequences to have.
But subsequences don't necessarily converge?
We're going to find out that if a sequence converges, every subsequence it has converges to the same thing.
Does your set of natural numbers have to be an infinite set of natural numbers?
Yes.
Okay.
Notice what we're doing. We're mapping, this is still just a sequence. It's mapping all the natural numbers to another natural number.
Right.
So yeah. So A sub n sub k still has just as many terms as A sub n.
Right.
They both have infinite. Okay, so any more questions about the definition of a subsequence? Okay, then let's see. Oh, I'm just saying note that this is general notation for a subsequence of A sub n. We already noted that. Okay, let's do our first proof, which is exactly what I said. So if the limit of A sub n is equal to A, then every subsequence of A sub n also converges to A. So let's do that proof. Proof if sub n is equal to a, then the limit of a sub n sub k of some subsequence, any subsequence, doesn't matter which one you pick, is also going to equal a. That's what I'm going to prove. Good? Understand what we're trying to prove? So 1, let a n be a sequence such that the limit of a n is equal to a. 2, sorry, we need to get our subsequence to, comma, and let a sub n sub k be any subsequence of a sub n. So we know a sub n is a sequence that converges to a, and a sub n sub k is just some sequence, any subsequence you want. If we prove that this also converges to a, then we're done. That's what we're trying to show. Good? And we're going to prove this directly. So how do we prove it converges? We prove that for any epsilon you pick, I can find an index such that from that index onwards, it's going to be within a, or it's going to be within epsilon of a. Right? Ultimately, I'm trying to get that a sub n sub k minus a is less than epsilon for all n greater than or equal to some big index. Or in this case, for all n sub k, sorry. Right? Whatever's right here. Okay, so ultimately that's what I'm trying to get, and we're done. So 2, let epsilon be any positive number. Let epsilon something greater than 0. 3, then there exists big N in the naturals such that the absolute value of a sub n minus a is less than epsilon for all n greater than or equal to that index. Since I know that a sub n converges to a already, then for any epsilon I pick, there has to be an index such that from that index onwards, this is true. Right? Let's see how I want to say this next part. Observe that n sub k has to be greater than or equal to n for all n in the natural numbers. Our subsequence, our sequence of increasing natural numbers, the nth term in it always has to be greater than or equal to the nth natural number. In other words, when you were giving me the sequence of, when you're saying n sub k, what could it be? The first term, the smallest number I could put here is 1. The next smallest number I could put here is 2. The next smallest number I could put here is 3. I can never put something smaller than what term we're on. The first term can't be smaller than 1, the second term can't be smaller than 2, the third term can't be smaller than 3, but it could be bigger. I can suddenly skip to 10 here. But now that requires the smallest thing my next term could be is 11. So notice, this is the first term, second term, third term, fourth term, fifth term. What I'm saying is that this number is always greater than or equal to this number. Make sense? So this is the whole trick to the proof. So I don't know if there's a better way to just say it than this. Then the absolute value of a sub n sub k is minus a is less than epsilon for all n sub k greater than or equal to n. And 6, I guess I can say it this way then a sub n sub k minus a is less than epsilon for all k greater than or equal to n. Maybe that's a better way to say it. Do you like that better? Let's see how I wrote it here. Oh. Is greater than or equal to k for all k in n. That still says the exact same thing that I said before. It didn't change it, just changed the variable.
That makes no sense.
Okay. Let's see what else I did to see if we can help clear this up. So we know that's this. I did this in a little bit different order for some reason. Yeah, that's pretty much how I had it. Guess we don't really need this line, huh? Anyways, there's the proof. Any questions about it?
I guess not.
Yeah, since this inequality is true for all a sub n from big N onwards, and since this term is always going to be as far or further in the sequence than this term, then all these terms are going to be further in the sequence or just as far, right? You see what I'm saying there? So we're good? Okay. It's not that complex of a proof, so if anything feels weird, we can hammer it. Let's see. Nope, we already made this note, but we'll note it again. Since a sub n plus 1 is a subsequence of a sub n, oh, yeah, then the limits are the same. So we just barely proved if a sequence converges, then every subsequence converges to the same thing. And I'm going to note this special case because I'm going to use it in the following proof. All right. So proof. Let's see. If a sub 1 is equal to 1 and a sub n plus 1 is equal to 1 plus a to the n over 2 plus a to the n, then the limit of a to the n is equal to 1 minus the square root of 5, or negative 1 plus the square root of 5, yeah, it has to be positive, over 2. Okay, so first off, let's get comfortable with what exactly this sequence is. We'll write that down here out of the way. What's the first term in the sequence? 1. What's the second term in the sequence?
2/3.
Yeah. The next term is equal to 1 plus the previous term over 2 plus the previous term. So when you plug in 1 for an, you get 2 over 3. All right, let's do one more. When you plug in 2/3 for an, what do you get? In the numerator, you're going to get 2/3 plus 1 is 5/3. And in the denominator, you're going to get 2 6/3 plus 2/3 is 8/3, right? And so you get 5/8. Right? So if I gave you a test question that said expand the sequence, you could expand the sequence, write it out. Okay, so that's roughly what our sequence looks like. And we want to say, what does this thing converge to? What does it get closer and closer to? We're going to prove it gets closer and closer to this thing.
I feel like we've seen that. Does that have something to do with like the old ratio? Or
Yes, it is somehow related, and I was going to figure out how. Because I remember this coming up too, and I didn't take the time to figure that out ahead of time. I might have gone over it in last year's lectures when this came up. I'd have to check that. But yeah, I know I've come across it before, or at least something that's very familiar to it, because I had the exact same feeling, and I thought the exact same thing, that somehow this is related to the golden ratio. I don't think it's the numeric value of the golden ratio, but then again, I don't know if the golden ratio is transcendental. You can search that real quick. Is the golden ratio transcendental? And that would answer our question. Or what's its numeric value? Anyways, why am I looking at that? Okay, so there's going to be two basic steps to this proof, and any proof that you ever get that's like this. The first thing we have to do is prove that this thing converges, and then once we know that it converges, then we need to prove that what it converges to is in fact this. So proofs like this have two parts to it. One, show first of all that it does converge. Two, show that the thing it converges to is this number. So first off, let's show that this thing converges. Let's see, do I want to do bounded first or monotone? So one, I say, observe that a sub n plus 1 is positive if a sub, is positive if a sub n is positive, and that a sub 1 is positive. So the first term in the sequence we know is positive, and we know that the second term in the sequence is positive if it's the next term in the sequence is positive if its previous term is positive, right? If this is a positive number and this is a positive number, we know that the sum of positives is positive, the sum of positives is positive, and the quotient of positives is positive. Therefore, the whole sequence is positive, right?
That just means that every term inside it is positive, right?
Yeah. Then 0 is the lower bound for the sequence. That's basically what I'm getting at. Because remember, I told you we're going to do two things. We're going to first show that this thing converges, then show the thing that it converges to is this thing. So if I want to show that this thing converges, from last week, what's the easiest way to show something converges? You just need to show that it's bounded and monotone. If it's bound from below and monotonically decreasing, then we know it converges. If it's bounded from above and monotonically increasing, then we know it converges. So I know that this thing is bounded from below by 0. So the next thing I need to show is that this thing is monotonically decreasing. The next term in the sequence is always less than or equal to the previous term in the sequence. Good? Okay, so I've got that's bounded from below. The next step is to show that it's monotonically decreasing. How do you show that a sequence is monotonically decreasing? You show.
You have I guess you could take an arbitrary term and show that it's less than the one before it.
Right, so what we're going to do is we're going to show that a sub n plus 1 minus a sub n is negative. If the next term minus the previous term is always negative, then it's always decreasing. And if it's always decreasing, it's monotonically decreasing. Does that make sense? All right. So that's what we're going to do. Then, let's see. A sub n plus 1 minus a sub n is equal to, now we've got this nightmare of an expression to work with, 1 plus a sub n. I'm going to do a sub n plus 2 minus a sub n plus 1. It's the exact same thing, right?
Yeah.
But it's just going to make so I can use, I don't have to write pluses as often. So let's see, a sub n plus 2 is going to be 1 plus a sub n plus 1 over 2 plus a sub n plus 1, plus 1 in the denominator, or in the subscript, minus 1 plus a sub n over 2 plus a sub n. Make sense so far? Now we're just going to do a bunch of algebra. So I need to get a common denominator, so I'm going to multiply this one top and bottom by 2 plus a sub n. And I'm going to multiply this one top and bottom by 2 plus a sub n plus 1. So let's see. So multiplying this by 2 plus a sub n, I'm going to get 2 plus a sub n plus 2 a sub n plus 1 plus a sub n plus 1 times a sub n. That's multiplying this into this. And now we're going to have minus, let's put parentheses so we can keep track of where everything came from. And then minus, I'm going to multiply this into this. So we're going to get 2 plus a sub n plus 1 plus 2 a sub n plus a sub n plus 1 times a sub n, and then our denominator is just going to be the product of these two. 2 plus a sub n plus 1 times 2 plus a sub n. Any questions so far? All right? Which is equal to, we're going to simplify. Notice the 2's are going to go out. And these are going to go out. Right? So then I'm going to have a sub n plus 2 a sub n plus 1 minus a sub n plus 1 minus 2 a sub n all over 2 plus a sub n plus 1 times 2 plus a sub n. Okay, we can still combine like factors. I have a positive a sub n here and minus 2 a sub n here, and then a positive 2 a sub n plus 1 here and a negative a sub n plus 1 there. So putting those all together, this is equal to a sub n plus 1 minus a sub n all over 2 plus a sub n plus 1 times 2 plus a sub n. Alright, I'm just going to write this and then I'll explain. Then, since a sub 2 minus a sub 1 is negative, then a sub n is monotonically decreasing. And I'll explain that. Okay, so notice, when is this term negative? When a sub n plus 1 is bigger than a sub n. Do I have that right? The next term minus the previous term. Oh, yeah, so when a sub n is bigger than a sub n plus 1, this is negative. So notice that this is negative going from, we got smaller going from n plus 1 to n plus 2, if and only if we got smaller going from a sub n to a sub n plus 1. So the difference of these two terms is negative if the difference of these two terms is negative. And since the difference of the first two terms is negative, this minus this is negative. So since the difference of the first two terms is negative, then when you plug that in, you're going to get the difference of the next two terms is negative. And then the difference of the next two after that is negative. So we could have done an inductive proof here, but this would be your base case. This is negative, and then this is always negative when this is negative. So observe base case, this is negative. Assume that this is negative, then this is negative. Therefore, it's negative for any natural number you choose. So the sequence is monotonically decreasing. You get with all the logic there? Say it one more time.
No, you said that the first term minus the second term is negative?
Yeah, 1 minus 2/3 is negative 1/3.
No, it's 1/3.
Shh.
The second term minus the first term.
Sorry.
Okay.
A sub 2 minus a sub 1, what I wrote, not what I said.
Okay.
2/3 minus 1 is negative. The next term minus the previous term is negative.
Right, okay.
And the two terms after that, their difference is negative if this was negative. And since the first time this happens is negative, then it's negative from there on out.
That makes sense.
Sorry, mixed up my words with what I wrote, but everything I've written on the board is correct.
Mm-hmm.
Okay, so therefore we know AN converges. So all of this was just show converges. We know it's bounded below by 0, and we know it's monotonically decreasing. Last week we proved any sequence that's bounded from below and monotonically decreasing converges. We also know it converges to its infimum, but all we need is the fact that it converges, right? So 6, then the limit of a sub n is equal to a for some a. So we know that this thing converges to some number a. Now we're going to prove that that thing it converges to is actually this number.
How do you do that?
Yeah, we'll see it here in a sec. And the trick comes from what we said here. The limit of a sub n plus 1 and the limit of a sub n are the same thing. Okay? So I know, since I know that this is equal to this, then the limit of this is equal to the limit of this. Then the limit of a sub n plus 1 is equal to the limit of 1 plus a sub n over 2 plus a sub n. You with me so far?
Yeah.
That's just from the very top. Okay, well we know that the limit of a sub n plus 1 is just a. Whatever a is, that's what it converges to, right? And if an converges to a, what does this whole thing converge to? That's just 1 plus a over 2 plus a. Right?
How did we get that?
For what this converges to?
Yeah.
The limit of a quotient is the quotient of the limits.
Right.
And then the limit of the sum is the sum of the limits. So what's the limit of 1? Just 1. What's the limit of a sub n? A. What's the limit of 2? 2. What's the limit of a sub n? A.
Okay.
And then the left-hand side should be more obvious, right? So we good? And now we have one equation, one unknown, just simple algebra now, right? Multiply both sides by 2 plus a, what do we get? 2a plus a squared is equal to 1 plus a. Get everything on the same side, so we've got an equation that equals 0. I'm going to write my a squared term first. A squared, we're going to have 2a minus a is just plus a, minus 1 is equal to 0.
That's nice and simple.
And now we just use a quadratic equation. So that gives us that -1 plus or minus the square root of 1 minus 4 times 1 times -1 all over 2.
Okay, wait, what are you doing?
The quadratic equation. So I have x squared plus x minus 1 equal to 0. We'll just scribble it right here. So quadratic equation. If I have ax squared plus bx plus c is equal to 0, then I know that x is equal to -b plus or minus the square root of b squared minus 4ac all over 2a.
Oh,
Quadratic equation.
alright, okay.
So that's all I'm doing to get from here to here. In this case, my a is my x, and these are just the coefficients for my terms. So the coefficient for my a squared term is just 1, so plug in 1 for my a's. Coefficient to my x term is 1, so plug in 1 for my b's, and then c is just -1, so plug in -1 for c. So I have negative the coefficient of a plus or minus the square root of the coefficient of a squared minus 4 times the coefficient of a, which is just 1, times c, which is -1, all over 2 times the coefficient of a squared, of a squared, which is just 1. Okay?
That's equal to a, right?
Yeah. Thank you. So I know a equals this, that's what it gives me. That gives me a is equal to -1 plus or minus the square root of 5 over 2. Now, let's see, I was trying to prove it's equal to the square root of 5 over 2. This says plus or minus the square root of 5 over 2. Now what?
Works just fine.
No, I need this as my answer. -1 plus the square root of 5 over 2. Here I have -1 plus or minus the square root of 5 over 2. How can I get from this, how can I justify?
You just erase the minus.
But how do I justify that that's valid?
Does it have to do with that -1 plus the square root of 5 has to be positive? That a has to be positive?
No.
The square root has to be positive, right?
Oh yeah, that's what I'm saying, so a has to be positive.
Oh, sure. Yeah, so an is bounded from below by 0. We know that if an's monotonically decreasing, and it's bounded from below, therefore it converges to its infimum, its greatest lower bound. We know that 0 is the lower bound, so what it converges to has to be greater than or equal to 0. So we can't have the negative there, because -1 minus the square root of 5 over 2 is smaller than 0. So we know 0 is the lower bound. We know that this thing converges to its greatest lower bound. Therefore, we can't have the negative option. Therefore, it's a positive option. So this thing converges to that number, whatever it is. Good? So that's how you'll do proofs like these. When it says prove that some sequence converges to a particular number, there's 2 steps to it. 1, show that the sequence converges to, then show it converges to that number. Unless you can show it converges to the number directly, right? Like when we prove that 1 over n converges to 0, then we just go straight to the epsilon delta definition. So I should say that anytime you have a problem like this is how you do it. But this is a way of doing problems like this. Okay, so that was that proof. Now, we'll move on to our next step. Sorry, you didn't have any more questions, did you? Okay, so now we'll move on to our definition of a peak index. A peak index in a sequence is the index for which that sequence only gets smaller from there on out. So,
is there a sequence where the peak index isn't 1?
it's not 1. 1 over 2 to the n. There's a sequence. So first off, let's go over it in general, and then, or let me do a picture for intuition of what peak is, because it might not be exactly what you're thinking yet. And then we'll go back to the definition exactly. So I'm going to graph some sequence here. So 1's going to go to something 2, 3, 4, 5, 6, 7, 8, etc. So let's say that my sequence looks something like this. It pokes up some, and then from here on out, it just keeps getting smaller. Something like that. You with me?
Okay.
So a peak index is an index where, from that point onwards, the sequence only gets smaller or stays the same. So notice that from this point onwards, it does not always get smaller or stay the same. From this point, it doesn't. From this point, it doesn't. But from this point, it does. All the points from here onwards are less than or equal to this value. Same with here. From here onwards, all the points are less than or equal to that one. Same with here, same with here, same with here, etc. So every point from here onwards is a peak index. So now let's read the definition exactly. Down here. We call M is the index this occurred at. So in this case, if this is a peak index, M would be 1, 2, 3, 4, 5. So we call M, or 5 over here, a peak index, provided that for all the indices after that point, the terms are smaller than or equal to what they were at M. For all n greater than or equal to m, a sub n is less than or equal to a sub n. Follow that? All right.
Why is it 4 the peak?
Why is it what?
Why is it 4 the peak?
4 is also a peak. 4 is a peak. This is also a peak index. This is a peak index. This is a peak index. This is.
Right.
They
but
all are
4
except
is
for
the
these
main
3.
one.
4 is the highest peak, but they are all peak indices.
Huh, okay.
It is always the case, if you pick 7, it is the case that for all the indices from 7 onwards, the value is less than or equal to what it was at 7. So from 7 onwards, here's the value at 7. It is the case that from here onwards, the values are always less than or equal to what they were at 7. So, quick question. This sequence, does it have any peak indices? No, there are no peak indices except for every even index. 2 is a peak index, 4 is a peak index, 6,
Oh, 'cause
8,
it's less than or equal to
10,
it.
12, because it's less than or equal to it,
Oh, shit.
right?
Oh.
What is a sequence? -1, 1, -1, 1, -1, 1. Is it the case that all the numbers from here onwards are less than or equal to 1? Yeah. What about from here? Yeah. What about from here? Yeah, etc. Every even index is a peak index. Let me try and come up with another weird example to make sure we're good on it. What about the sequence just 5? 5, 5, 5, 5, 5, 5, 5, 5, 5.
Yeah.
Yes.
What are the peak indices?
Everything.
Every peak index. Not the peak value, peak indice.
5.
Yeah, so we're looking for the m such that a sub m is greater than or equal to all the terms. So we're talking about an index. Don't get confused between the index and the actual value. Because now that you say that, I remember that was a problem last year. They kept getting mixed up between a peak index, talking about an index, not the value at that index. It's just an index. Okay. So, peak index, think you got the feel for it. Next. Every sequence contains a monotone subsequence. Every sequence contains a monotone subsequence. So for any sequence you pick, I can always find a subsequence of it that's monotone. So let's pick a sequence that's not monotone. Give me a sequence that isn't monotone.
-1 to the end.
The one you
-1 to the end, perfect.
Yeah.
So -1 to the end. What is a monotone subsequence I can get from there?
1, 1, 1, 1, 1.
Yeah, -1 to the 2 end. There's our subsequence. We pick every second index from this, and that gives us 1, 1, 1, 1, 1. Huh?
How was that monotone?
So then this is equal to just 1, 1, 1, 1, 1.
Right. What's the definition of monotone?
So a sequence is monotonically increasing if the next term in a sequence is always greater than or equal to the previous term. A sequence is monotonically decreasing if the next term is always less than or equal to the previous term. And then a sequence is monotone if it is either monotonically increasing or monotonically decreasing. So I look at a sequence. If I can come up with a monotonically increasing or a monotonically decreasing subsequence, then I have a monotone subsequence. Good? So is this one, what is this? Is this monotonically increasing?
It's both.
Yeah. It's also monotonically decreasing. It's both. Okay. Well, good enough. We won't worry about it. So, let's see. Let's just do the proof now. Every sequence contains a monotone subsequence. Every sequence contains a monotone subsequence. Alright, 1. Let a sub n be some sequence. 2. Observe that a sub n either has infinite or finite, has an infinite or a finite number of peak indices. Indices. How do you spell indices?
ICS.
I-C-E-S.
No, sorry. It's I.
Oh, yeah, indices. There we go. All right. So, pick any sequence you want. It either has finitely many peak indices or infinitely many peak indices. Wait, what if it has 0 peak indices? Isn't that possible?
No.
It is possible. Look at the sequence n. 1, 2, 3, 4.
Oops.
Oh, right.
Then it is fine.
0 is a finite number.
Yeah.
Okay? So any sequence either has infinitely many peak indices or it doesn't have infinitely many peak indices, meaning it has finitely many peak indices. Maybe 0, maybe 10, maybe 100. But the number of peak indices is either infinite or it's finite.
Wait a minute, wait, what? What do you mean? 1, 2, 3, 4, 5, 6, 7, 8. That doesn't have any.
Right, so it has 0. 0 is a finite number. So the number of peak indices it has is 0, which is finite.
Okay.
So I'm saying any sequence you pick, it either has infinitely many peak indices, like 1 over n, or -1 to the n. Both those have infinitely many peak indices. Or it has finitely many peak indices. Here's an example of one that has finitely many. You good? So I'm going to show that in either case, I can find a monotone subsequence. Good? So if a sub n has infinitely many peak indices, comma. Okay, so if it has infinitely many peak indices, then what does that mean?
It's monotonically decreasing.
If we just pick those peak indices, then we're going to end up with a monotonically decreasing sequence, right? So if a sub n has infinitely many peak indices, comma, then let n sub k be the sequence of those peak indices, something like that. You with me? Then, I don't know, see if you're good with this. If not, we can do more explanation. Then a sub n sub k is monotonically decreasing.
So does it have to be the sequence of peak indices? Because it seems like
It doesn't have to be. We just need to find one subsequence that works. So if I know that this is a sequence of peak indices, what does it mean to be a peak index? It means from this index onwards, all the terms are less than or equal to the current term. So a sub n sub k is always going to be greater than or equal to its next term, a sub n sub k plus 1. Because a sub n sub k is a peak. Do you understand that, or should we write that out one more line? Add a line?
Sure.
All right, let's add a line. Since n sub k is a peak index, then a sub n sub k is going to be greater than or equal to a sub n sub k plus 1. Right? Since n sub k is a peak, then the value at this peak has to be greater than or equal to the value at any point later in the sequence. Okay, fine. Therefore, it is monotonically decreasing. Therefore, a sub n sub k is monotonically decreasing. Okay, so we found if a sub n has infinitely many peak indices, we found a subsequence that is monotone. Now I need to handle the next case. If a sub n has finitely many peaks, comma, then there has to come a point in the sequence where from that point onwards we no longer have any peaks. So if a sub n has finitely many peaks, then there exists some index n such that, how do I want to say it? Let me see how I wrote it in my notes. But basically from that point onwards, we don't have any peaks.
And then we don't have any peaks, so not from that point onwards, right?
I said it. If a sub n has finitely many peaks, then there exists some n such that there exists some n in n such that big N is the last peak index.
That doesn't make sense. Is the only peak index?
It's the last one. So if
Oh, right, okay.
okay. Okay. So 7. Now I'm going to start creating my my sequence of indices that I'm going to use to create my subsequence. So I'm going to start creating my n sub k.
If your sequence doesn't have any peaks, then what index would be the last peak?
0.
But isn't n a natural number?
Okay.
And not equal to 0.
Yeah, so the way that I define my n sub 1 also works, so maybe I'll make a note. If n does not exist, then epsilon 1 can just equal 1. Something like that. So then n sub 1 equal to big N plus 1 is not a peak. And then something like, note if no such n exists, then n sub 1 equal to 1 is not a peak. So we're going to say that n sub 1 is the first index after our last peak. If there was no last peak index, then we'll just say n sub 1 is just the first one.
You can just do that.
Why not? I'm just coming up with n sub k. What is a sequence? So I'm saying the first term in this sequence is going to be the one after my last peak. If there was no last peak, then just make it the first term in the sequence.
Oh.
Good?
Yeah.
Okay. So now I need to figure out how to come up with my n sub 2. So 8. Since n sub 1 is not a peak, what does it mean for it to not be a peak?
Everything after it is increasing.
Not everything, but something after it is increasing.
Oh, yeah.
It could go down after it, but if it eventually gets higher than our peak, we didn't have a peak. So since n sub 1 is not a peak, then there exists n sub 2 in n such that n sub 2 is greater than n sub 1. So there exists some index later in the sequence where the value at that sequence, a at n sub 2, is greater than a at n sub 1. Right?
Okay.
That's what it means to not be a peak. If n1 is not a peak, then there is some other index called n sub 2 such that the value at that point, the value at n sub 2, is greater than the value at n sub 1. So in other words, if my sequence, if we were to plot the point of my sequence and it looks something like this, I know that this point right here is not a peak, so its index, n sub 1, is not a peak. That means that there is some later index. We can use any one we want. We'll pick this one. There is some later index, n sub 2, such that the value at n sub 2, a at n sub 2, is greater than a at n sub 1. You see it? Okay. Am I just over explaining?
Probably, because I understood that. I was just wondering why we needed to say that.
I'm trying to create a monotonically increasing sequence now. Right, it doesn't matter if it's monotonically decreasing or increasing. So if there were infinitely many peaks, I found one monotonically decreasing. If there's finitely many peaks, I'm going to find one that's monotonically increasing. And then again, or similarly, or whatever you want, just so we're not doing a proof by induction. So similarly, since n sub 2 is not a peak, then there exists n sub 3 in n such that n sub 3 is greater than n sub 2 and a at n sub 3 is greater than a at n sub 2. In general, since n sub k is not a peak, well, I don't know if I want to say that. I think you get the point
with those
here.
examples, you could just say, therefore, a sub n is less than a sub n plus 1. And then you have your definition of decrease. Or
Yeah, then I can say then n sub k is a sequence of increasing naturals such that a sub n sub k plus 1 is greater than a sub n sub k. 11. Then a sub n sub k is a monotonically increasing subsequence of an. Right? I mean, you're right. Good?
Yep.
Alright, so that is the proof that every sequence contains a monotone subsequence. Okay, now we're going to prove that every bounded sequence has a convergent subsequence. Okay, that's going to be easy.
We can just show that the bounded sequence is a subsequence of the self-changing. Oh, no, because that might not converge.
For this one, every bounded sequence has a convergent subsequence. So if a sequence is bounded, its subsequence is bounded. Every sequence has a monotone subsequence. So every bounded sequence has a monotone bounded subsequence. And every monotone bounded sequence converges.
Mhm.
Do we even need to write that, or just saying that, was that enough?
Was enough for me.
Makes sense. And that's just
I mean-
the 3 steps to the proof, right?
Yeah.
Yeah, it's a 3-line proof. Literally,
We might as well just write it.
I have 2 lines there. Might as well just write it. Okay. We can write it. All the markers over here are green, but different shades. Proof. I don't know why I'm holding that. We don't care. I have it right here. Every bounded sequence. Every bounded sequence has a convergent subsequence. Okay. 1, what's the first line going to be?
Let a n be a bounded sequence.
Let a n be a bounded sequence. Okay. And then, now what?
Then AN has a monotone subsequence.
Right. Then there exists A sub n sub k, some subsequence of that, such that
It's
A
bounded,
sub n sub k is monotone.
except we don't really,
Okay, so we got A sub n sub k is monotone. Now what?
the subsequence of a sequence is bounded.
Right. 4. Oops. 3. Since A sub n is bounded, then A sub n sub k is bounded. Do you understand why exactly this is true and it's not just appealing to your intuition?
Well, how can A sub n sub k have a term that's
Right,
outside
all the
A sub n?
terms in here are in here. So if all the terms in here are bounded, all the terms in here are bounded. Okay. Alright, so then what?
Or therefore A sub n sub k converges.
Therefore, A sub n sub k converges. And we're done. Right? Okay.
Is that everything?
Was that all the?
No. It's almost everything. We have one more definition, 2 example proofs using the definition, and then one more proof that's an actual proof that you'd use in future proofs. Alright, so maybe I'll get resituated over there and I'll write the rest of the stuff to the side that we're going to be doing. So you can go on break and I'll get set up for the class a little bit. Huh?
Is it K?
Be sure to go stand outside for a bit if you're feeling tired.
Happy birthday, by the way.
Thank you. Is that today? It is today.
Nice.
Yes.
How old are you now?
Too old.
29?
No.
28?
Yes.
I thought you were 28 this whole time, that's so weird.
So did I actually until I stopped to think about it. Can I? Well, actually, maybe.
Yeah,
It should be fine. I can zoom in.
yeah, I got a text from Michaela this morning. How's it going? She's like, it's Donnie's birthday today.
Yeah, it's a lot more important to her than it is to me.
Birthdays are important.
I failed to see
It's
why.
good to just celebrate the day you were brought into this earth. Because every other day, it's not really about you.
I don't need any day to be about me.
Sure you do.
Sure I do.
It's good for people.
I don't know why. How's our red? Actually, that green was already okay. This one? next week, don't we?
Mm-hmm.
Need to make that.
So you have everything assigned just for the first semester, right?
Yeah, I only have the first semester up.
First semester. Okay.
Made the mistake one year of putting up a year's worth, but the system clears itself at the end of a semester.
Oh, second.
Yeah. So.
We don't have Veterans Day off, do we?
I don't have a clue. Is that a Tuesday?
That's tomorrow.
Tomorrow. Yeah.
We're not gonna have enough time for our chapter 3 test and our midterm.
We'll figure it out. I'll look at the calendar, and if we're still behind, I'll probably just do start chapter 3 material next week and just make the test take home again to get a week back.
Yeah, that would be
Yeah, to count out the calendar. Because the only one I really want for sure you guys to do here is the midterm.
yeah.
keeps on chugging away. Chapter 3, finally gonna start some calculus talk. Continuity. Maybe I'll just start writing proofs. We ready to continue?
Yeah.
Okay. So go through these definition first, then the proofs. Okay, definition. So this is one of those definitions that feels kind of weird, but ends up being useful. Okay, a set of real numbers S is said to be sequentially compact, provided that every sequence in S contains a subsequence that converges to a point in S. So notice sequentially compact is a property on a set of numbers, not a property of sequence. So a set of numbers is sequentially compact if every sequence that you can get in that set of numbers has a convergent subsequence that converges to a point in that set. Not has a subsequence, but every subsequence that converges to a point in S. Read it one more time, because I think I said that wrong. A set of real numbers S is said to be sequentially compact, provided that every sequence AN in S contains a subsequence that converges to a point in S. Okay, so I said it right the first time.
Okay.
Every sequence that contains a subsequence that converges to a point in S.
Will you just give like a quick example of that?
Yeah, we'll do 2 examples showing things that are not sequentially compact, and then one proof showing that it is. So open interval 0 to 2 included is not sequentially compact. This set of numbers is not sequentially compact. If it's not sequentially compact, what does that mean? That means that we can find a sequence in here. We can find a sequence such that every subsequence of that sequence converges to a point outside the set. So, proof 0 not included, 2 included is not sequentially compact. Observe that 1 over n is a sequence in here, right? And that the limit of 1 over n equals 0. Well, we know that if a sequence converges, then every one of its subsequences converges to the same thing. So then the limit of every subsequence of 1 over n is also 0, which is not in there. So 1 over n is a sequence such that all of its subsequences converge to a point outside the set. Therefore, the set is not sequentially compact. What does it mean for it to be sequentially compact? A set of real numbers is sequentially compact, provided that for every sequence you find, it contains a subsequence that converges to a point inside the set. So to show that it's not, we need to find one sequence such that for every subsequence, it converges to a point outside the set. In this case, we picked 1 over n. Let's do another one. Closed interval 0 all the way to infinity is also not sequentially compact. Let's example here. Observe that just the natural numbers is a sequence in here, right? And every subsequence of the natural numbers is going to be unbounded. And if a sequence is unbounded, it doesn't converge. Therefore, the sequence of natural numbers is a sequence that does not have a convergent subsequence. Therefore, it definitely doesn't have a subsequence that converges to a number in the set. So, in order for it to be sequentially compact, every sequence has to have a convergent subsequence that converges to a point in the set. Okay, so then, natural question, what types of sets are sequentially compact? The answer is going to be sets like this, closed intervals. So next we're going to prove that these closed intervals are sequentially compact. I don't know how big this proof is. How much space do I need? 5 lines there. We should have space. Okay. Proof the closed interval AB is sequentially compact. 1. Let AB be a closed interval and let A sub n, let's not use A since we have an A there, x, let x sub n be some sequence in AB. What am I trying to show? I'm trying to show that x sub n has a subsequence that converges to a point in AB. If I can show that x sub n has a subsequence that converges to a point in AB, then I'm done. It's sequentially compact, right? Okay, so if x sub n is in AB, what does that give me? Then we know that A is always less than or equal to x sub n is less than or equal to B, which gives us that x sub n is bounded. Right? Now we know that every bounded sequence has a what?
Bounded subsequence.
Has
A monotone subsequence. Right? every bounded sequence has a convergent subsequent.
Oh, so right above it.
What?
Every sequence is in
Right, because it's bounded and monotone.
We can go straight to this.
Yeah.
Okay, cool.
Okay. Yeah, okay, that was combining them. I don't think I did that in my proof up there. Okay, we know every bounded sequence has a convergent subsequence. So then we know, then there exists some subsequence x sub n sub k such that the limit of x sub n sub k is equal to x for some x in R. In other words, the limit exists. So we know, since x of n is bounded, and since we know every bounded sequence has a convergent subsequence, then there must exist some sequence such that it converges to some number x. Right? Okay. What are we trying to show? We're trying to show that x is in AB. So since x sub n sub k is in AB, then x is in AB. You remember this proof? We proved that if a closed interval contains a sequence that converges, then what that sequence converges to is also in the closed interval. That's what it meant for it to be closed. That was our definition of closed. Let me find that exactly real quick. It wasn't there. I think it's 2.2. Yeah, a set S is closed if and only if, for every sequence in S, its limit is also in S. And then we proved that and we also proved that the closed interval AB is a closed set. So we proved that this was closed, and the definition of closed was every sequence in there that converges to a point in there. So since this is in here, then what it converges to is in there. And therefore it's sequentially compact. 5. Therefore, AB is sequentially compact. And we're done. And that's the end of 2.4, and that's the end of the chapter. So we'll have our test next week on all this, and we'll be ready to continue on our way in the material.
Do you think you